In this video, we're going to look at how we could calculate the change in entropy for a given reaction. So let's say we had a reaction such as the decomposition of calcium carbonate. That yields calcium oxide plus CO2 gas. And there's an equation for this, which is that the delta S is equal to the total. Remember, this Greek letter sigma means sum or total. So the sum of the entropy values of the products minus the sum of the entropy values for the reactants. This is going to work a lot like the delta H equation that we've seen in the past, sum of products minus sum of reactants. We're going to do all the exact same things. We're going to multiply by coefficients because these are going to be values per mole. And then we're going to make sure that this minus sign is used to flip the sign of whatever the total S value is for the reactants. All right, so let's just do this example here. So we go and we look up the entropy values for the molar entropy values for each of the compounds in the reaction. All right, and these are in tables, or if I forget to give you one, you're always welcome to look them up using the Google. So these are going to have units of joules per mole Kelvin. And let's see, CO2 is 213.7. Now, there's an interesting point to notice right off the bat, which is that notice that the gas CO2 is more than twice the entropy of either of the solids present. And this is going to generally be the case that gases have the most entropy. And so producing a gas is usually going to lead to a positive delta S, but here we're going to calculate the actual value and make sure. So we do our delta S is equal to the sum of our products, which is going to be 39.75 plus 213.7, minus the sum of our reactants. We only have one reactant. And this is going to all have units of joules per mole Kelvin. So get out our calculator, add all this up. And that gives us a value of positive 160.55 joules per mole Kelvin. All right, so these are generally speaking going to be pretty straightforward calculations. What's most interesting, as is almost always the case, is the sign here. We have a positive delta S because our products have more entropy than our reactants. And we could have predicted that beforehand because we're evolving a gas here, a mole of gas here, whereas we had no moles of gas on the reactant side. So this is how we calculate changes in entropy. We're going to use this equation. We're going to look up the tabulated values for entropy, and then we're going to plug them in. We're going to look at the sign and make sure that that makes sense with whether they're solids or gases, or rather gases being used or created in the reaction.